Hello friends, this video is brought to you by www.muayteaching.com.
Circles. In this chapter we will start with tangent to a circle. Then we shall move to number of tangents from a point on a circle and do certain theorems on it. Further we shall do certain examples based on these theorems. We have studied in previous classes that a circle is a collection of all points in a plane which are at constant distance from a fixed point, that is center. In this class, let us examine the different situations that can arise when a circle and a line are given in a plane. So let us consider a circle and a line in a plane. Then there can be three possibilities. Either this line will have no common point with the circle, or it can intersect the circle in two different points, or it can just touch the circle at one point. In the first case, when the line has no common point with the circle, we say that L is non-intersecting line with respect to the circle. In the second case, when there are two intersecting points of the line and the circle, we say that line N is the secant of the circle. And the third case, when there is only one point which is common to the line and the circle, we say that line M is tangent to the circle. In this chapter, we will study about the existence of the tangents to a circle and also study some of their properties. Let us illustrate that there is only one tangent at a point of the circle. Say we draw a tangent AB at a point P of the circle. Let us draw some more lines passing through point P. We can see that this line is intersecting the circle at point P and another point. If we observe all these lines closely, we see that all of them intersect the circle at another point other than P. Even the nearest line, the red one, intersects the circle at another point other than P, which implies that there is only one tangent at a point of the circle. Let us perform another activity and see what it leads to. On a paper, draw a circle and a secant PQ to it. Now draw various lines parallel to the secant on both sides of it. We observe that two points of intersection of the line and the circle are coming closer and closer as we move away from this line on both sides. And in one case, the distance between 2 points becomes 0 on one side of the secant, and another case it becomes 0 on the other side of the secant. In other words, these two are tangent to the circle parallel to the given secant PQ. Hence we come to the conclusion that the tangent to a circle is a special case of the secant when the two endpoints of its corresponding chord coincide. Also, we observe that these tangents are drawn parallel to our secant PQ. This brings us to another conclusion, that there cannot be more than two tangents parallel to a given secant. We now come to the proof of very important theorem, which says that the tangent at any point of a circle is perpendicular to the radius through the point of contact. If O is the center of the circle, then if we draw the radius from the point of contact P, we shall prove that OP is perpendicular to the tangent XY. Let us start with the proof. We need to prove that OP is perpendicular to XY. Let us take a point Q on XY other than P and join OQ. We have taken point Q outside the circle, since if Q lies inside the circle, then XY will become secant and not a tangent to the circle. Therefore, now we can say that OQ is greater than the radius of the circle, which is OP. If this point Q is anywhere else on XY other than at P, the inequality will apply. That means that OP is the shortest distance of the point O to the points of XY. But we know from our previous knowledge that perpendicular is the shortest distance of a point from a line, implying that OP is perpendicular to XY. Hence, we have proved the theorem that tangent at any point of a circle is perpendicular to the radius through the point of contact. And we have a remark which says that the line containing the radius through the point of contact is also called normal to the circle at that point. That means OP is also called the normal